ಎಲ್ಲ ಗೆಳೆಯರಿಗೂ ಶುಭ ಮುಂಜಾನೆ. Atoms, Bohr atom, the properties of electron, different characteristics that we have discussed, right? Today, the most important aspect of Bohr atom, the hydrogen spectrum, will be our topic. In fact, range of questions are possible from this, and for entire range of questions, two important tools I will today present for all of you. I said there are tools. What are those tools and how we will make use of that? Now let us start our session with all your preparedness, notes ready with you, textbooks ready with you. Start. Boys, a cool topic on a hot day, the atomic spectrum. Now the starting point for this would be the third postulate of Bohr, the transition of electron. Electron, when absorbs energy, it exits from lower energy level to higher energy level, right? But we know that this higher energy state is always unstable. Therefore, that is only for nanoseconds it stays there. So immediately, in the process of attaining stability, yes, higher orbit electrons, whenever they have this chance and possibility, they de-excite. They de-excite means higher energy level electron jumping to lower energy electron. That de-excitation is our basis, and for the de-excitation, what is the postulate? For electron de-excited from N2 higher level state to N1 lower energy stage, then this difference of energy, which I am writing as E2 minus E1. See, these numbers 1 and 2 should not refer as first orbit and second orbit. What I mean to tell you, you see, it is from the principal quantum number N2 to principal quantum number N1, any number, maybe 3 to 1, 4 to 2, 2 to 1, 3 to 2, any such thing. So it is from N2 state to N1 state. The difference of energy, of course, the conservation of energy, the difference of energy in the form of photon with the definite wavelength. Because we have seen in the case of atoms, the energy levels are discrete. It is having very different value depending upon the species of the atom. Hydrogen, the numbers minus 13.6 or whatever other numbers that we have given, that will be unique for hydrogen, and for any other atom it will be unique for that. Therefore, this lambda having specific values, atomic spectra, is always a line spectra because of discrete energy levels and discrete wavelengths. So this is Hc by lambda E2 minus E1. Now we are using that energy expression that we have derived yesterday. We have given one expression. You remember, energy of nth orbit final expression was RCH, R for Rydberg constant, C the speed of light, H for S Planck's constant, times 1 by n1 square, 1 by z square by n square. It was the final result. Now I am using that for E2 minus E1. This Hc by lambda equal to RCH is the common thing, 1 by n1 square minus 1 by n2 square. Of course, we have also this z square term. Remember, if it is hydrogen, then this value is of course 1. But I have told you Bohr atom, single electron atoms such as helium plus, lithium 2 plus, beryllium 3 plus. 99% of the examples we always see the case of hydrogen atom, but sometimes it will be other atoms also, and that is why, remember, this z square is also important. Now, in the following discussion, I will take up only the case of hydrogen. Therefore, this z square I will take it as 1. Otherwise, your data should tell you whether this value is 1 or any other number. Now, this is the first tool I was talking about. Hydrogen spectrum, range of examples. First tool is this expression. And what you find is that, of course, you will know Hc gets cancelled. Therefore, the only thing that remains is now 1 upon lambda, right? 1 upon lambda is R times. See, for this convenient only, that energy expression is rewritten in terms of Rydberg constant. I have told you to remember the number. You have to remember that number. So 1 by lambda, which we call wave number, Rydberg constant times 1 by n1 square minus 1 by n2 times z square. This 1 by lambda is there. Again, the units are important. Meter inverse, supposing somewhere centimeter inverse, convert them into meter inverse. Rydberg constant also with the units. See, this is our first tool. This is our first tool. If student is ready with this tool, yes, any range of examples are possible. Now the second one is understanding about those electronic transitions, the de-excitation of higher orbit electron to the lower orbit electron. Here again, one important beautiful picture, though you know your textbooks and your class notebooks will have one more time writing. When I am doing that, you please follow each and every line that I am going to draw. Now, the energy level diagram we have given for this hydrogen, supposing this is what is N is equal to 1 with minus 13.6 we have said, right? Even for any other case also we have that Z square by N squared term. Now I am writing particularly for hydrogen spectrum, right? This is the ground state which we call ground state, the lowest energy that is possible, and you know that the total energy of orbital electron is negative because of the bounded nature, yes? N is equal to 1 and there comes another N is equal to 2. Actually the length of the board is not supporting me, otherwise this difference should be still more higher difference we have to show. Now N is equal to 2, and as you know that as the order of the principal quantum number increases, energy difference separation decreases. Therefore here I show this is what is N is equal to 2. Strictly speaking, these are not the actual scales I am writing. I am just doing it as a model. And this is what is N equal to 4, and this is what is N equal to 5. Can you see? Gradually what you observe is that the difference between the spacing between the energy levels, I am showing it lesser and lesser and lesser. This is how it goes. This is N equal to 5, N equal to 6, and further N equal to 7. And then we have the continuum which we call very close spacing of those higher valence orbits. Now here, what are the different de-excitations that are possible? This is the key and this is the second tool. The tool one, you have to remember this expression, and then you have to remember this terminology also. What is the terminology with writing? The different possible de-excitations. Second orbit to first orbit. Now I am showing all those de-excitations from higher level to ground state which is N1 is equal to 1. Higher to ground, what are the different possibilities? 2 to 1, yes, 3 to 1, yes, 4 to 1, and so on. Such that the last one is that from continuum, which we call free electron, right? The valence orbit which we are taking. That continuum I will show it with dotted lines. So this is what is the terminology now you see. All these de-excitations are happening from higher to first orbit. All such de-excitations, that particular set of wavelengths is what is called as Lyman series. This is Lyman series. Lyman series. So Lyman series, the excitation value N1 is always 1 and N2 value starts from 2, 3, 4, so on, such that this is the first line of Lyman. 2 to 1 is the first line. Now in a given series of wavelengths, the set of wavelengths, we should have the understanding of what is this first line or last line, third line, fifth line. This is what is the key. This cannot be a memory, I am telling you. The memory should be this entire de-excitation diagram that we are showing is a tool. 2 to 1, first one. 3 to 1, second line. 4. So that is how you will do. That is, afterwards we will give that one more simple tabular column. Now all these excitations in which I have shown this dotted line. This dotted line represents the last line. Dotted line represents last line of that particular series, such that now follow some things so that finding right answers and options and without confusions it will be possible. What is that? We will see. See, first line to last line, let us follow the order from first line to last line. What is that we observe? First line to second line, energy difference increasing, right? This is what is observation. With that clue, I will now give a statement. first line to last line. Frequency of that particular line increases. Frequency of that particular line increases. Wavelength decreases such that first line minimum frequency and hence maximum wavelength. Last line maximum frequency and hence minimum wavelength. So these are what are called as limits. The minimum values, maximum values. When it comes to the question of minimum and maximum, look at whether it is frequency term or wavelength term. Minimum frequency, right, from first to last, frequency increasing, wavelength decreasing. So this is what is called as the limit value. The dotted line that I have shown you will tell you the limit value of that particular series. A question is asked. The limiting value in that particular series, suppose we call it 11, let us also see the case of other series as well, right? Now, let me show one more particular series. Now, earlier we said in this case higher to first orbit, the ground orbit. Now, what are the other possibilities? Yes, de-excitation from higher orbit to second orbit only. Remember, we are writing all different possibilities. Not that all these things happen in an order, in a sequence, not like that. All the different possible de-excitations we are now mentioning here. 3 to 2, 4 to 2, 5 to 2, right? Is it not? And similarly, you can say I will like one dotted line which is the limiting value. One more time, you will see a set of wavelengths where the de-excitation is happening from higher to second orbit. And this particular is what is called as Balmer series. This particular is what is called as Balmer series. See, there are specialties for each and every series which I will mention at the last part of our discussion. You just go through first about the de-excitations. Again, Balmer means N1 is equal to 2. Now, Balmer means N1 is equal to 2, not 1. In the case of Lyman, you see, remember, N1 is equal to 1 and N2 value is after 1, whatever that number, 2, 3, 4, so on, those integers. Balmer series N1 is equal to 2 and N2 is equal to 3, 4, 5, so on, the integers. So first line of Balmer, second line of Balmer, second line of Lyman. These transitions are very important. Once you are clear about the transition, I am telling you, you're 1 in 1 lakh. Definitely I can say 1 in 1 lakh. Those examples you will do, which are in fact not a cup of tea for most of the students. De-excitation process. The third one. Now you can go on doing that. You can go on doing that. Therefore now, using this as a model, now I will mention a simple tabular column. Right? Those tabular column, again I will see it for Lyman and Balmer. Other three things also you can do on your own. Let us see that one more time. The first series we thought is Lyman series. Lyman series, N1 value is 1. Remember what is N1? The lower energy level. That principal quantum number is N1. N2 is the higher principal quantum number of higher energy stage. Now what is N2 value? I have told you after 1, 2, 3, so on. The last number is what is infinity. So find that limiting value when we are writing for wavelengths, limiting value whenever you see limiting, maybe again without confusion whether it is first line or last line. First line means N2 is equal to 2. Likewise, like last line means N2 is equal to infinity. That is what is the limiting value. Now all these frequent wavelengths that we get or frequencies that we get, this Lyman wavelengths will be in ultraviolet region. UV region wavelengths radiation will be observed in Balmer series. And remember, in the entire hydrogen spectrum, Lyman series is the only series, the set of wavelengths in the UV region. Now, as I have told you, this is the UV region, number 1 and number 2. The first number, second number, third number, last number. So these things are also an important thing. Now after Lyman series, now please you do calculate. We have already this 1 by lambda numbers, you see. So what is that lambda minimum, what is that lambda maximum? Once you are getting lambda minimum and lambda maximum, you can do it for frequencies because f is equal to c by lambda. So this is what is the approach, right? You want me to show one? Yes, for one particular series I am showing you. So supposing first line, I am writing the first line 1 by lambda is equal to r into 1 by 1 square minus 1 by 2 square. This is 1 minus 1 by 4, which is 3 by 4. Therefore, this is what is lambda is equal to 3r, sorry, you will get it as 4r by 3. Is it not? Lambda is equal to 4r by 3. Remember, first line is always with maximum wavelength and minimum frequency. First line to last line, frequency increases, wavelength decreases. Therefore, the first line, maximum wavelength, minimum frequency. So this is what is lambda maximum value. And do remember, you have to substitute the r value with your memory, and I don't do that. Lambda maximum, and therefore what will be the frequency minimum? Frequency minimum, we know that frequency is nothing but C upon lambda. C upon lambda, which is lambda maximum. Therefore, what is your answer? You will get it as 3C by 4R. 3C by 4R. All SI units, C value, speed of light 3 into 10 raised 8, and R value, write it on your own. Every time I am not telling you this is Rydberg constant, because go through your class notes, textbook, and please practice that number 3C by 4R. This is maximum wavelength and minimum frequencies. And similarly, you can also calculate what is that lambda minimum. Lambda minimum means, here lambda maximum means N2 is equal to 2. N2 is equal to 2, we get lambda maximum. Lambda minimum we get for N2 is equal to infinity. The last line I have told you, for any series we are writing the N2 last line is always N2 infinity. Therefore that lambda minimum is equal to, you will simply get it as 1 by r, because this is 1 by 1 square minus 1 by infinity 0. Therefore lambda minimum is equal to 1 by r. So this is how you also compare the lambda minimum and lambda maximum for a given series. The same can be questions as I have told you, wide range. Minimum wavelength in one series compared with maximum wavelength in the other series. What not? Different types of comparisons that increases the range. And that is why, as I have told you, if we remember this as a tool and this de-excitation as a second tool, it's really an answer in 30 seconds that we get. So this is how we calculate the particular wavelengths or frequencies. I have shown for first and last. Now it can also be called third line of Lyman. What is the third line of Lyman? We should have a meaning. Third line of Lyman means 1, 2, 3. See, that is 4 to 1. So that kind of, again I am telling you, not a memory. It is a logic that which you have to build your tool. Now let me show now the other different series in the hydrogen spectrum. The second one is, I have told you the Balmer series, and now for Balmer series, N1 value is, I have told you 2, because higher orbital, second orbital excitation. Therefore it will be 3, 4, 5, so on, the infinity. And Balmer series, all these wavelengths will be in the visible region. Remember, all these wavelengths will be in visible region. Lyman series was in UV region, and that is the only series in the hydrogen spectrum which will lie in the UV region. Balmer series is the only region that lies in visible spectrum. Visible spectrum, one and only Balmer. Ultraviolet, one and only Lyman, like that. Now here again, Balmer series, first line, second line, last line, minimum wavelengths, maximum wavelengths, limiting values, frequencies. You can do it as earlier I have shown you. Lyman series, Balmer series, Pastel series. Pastel series, here 3, therefore 4, 5, 6, so on, infinity. Then comes bracket series, B-R-A-C-K-E-T, bracket series 4, and then higher numbers 5, 6, 7, infinity. And last one is what is fund series, P silent, you know. Fund series. And N1 value is the next number, which is 5, and other things are 6, 7, 8, so on, infinity. That is how we will see. And now, this is the only one in the visible, UV region. This one is in the visible region, UV region, visible region, and all these regions will be in infrared region, IR region, such that when it comes to P-fund region, it will be in far infrared region, P-fund series. This Pastel and bracket will be in infrared region, and P-fund will be still higher wavelengths that we get, so it will be in far infrared regions. For in each of the series, the first numbers, last numbers, minimum, maximum with respect to both wavelengths and also frequencies. Comparison of one series with the same, comparison of two wavelengths in the same series, or comparison of two wavelengths in different series, whatnot, everything is that. Now when you follow this discussion, look at this number, look at these numbers. One thing you can infer that in the entire hydrogen spectrum, where you are getting the most energetic photon, highest frequency, which series? Supposing a question, a simple CD question, simple commentary question. People say that it is conceptual and confusion. This is what is the tool I have given you. No confusion whatsoever now. Maximum frequency means maximum energy. Maximum energy means highest spacing between these energy levels. Therefore, you can see Lyman series. When you get Lyman series, the last line of Lyman is the most, maximum frequency of the entire spectrum is nothing but last line of Lyman. Maximum frequency corresponds to minimum wavelength. Therefore, in the entire hydrogen spectrum, the minimum wavelength is, it can be answered, that is the last line of Lyman in terms of frequency, the highest frequency, the maximum frequency. And now similarly, when it comes to fund question, fund series, which is in the Ford infrared design, as I have told you, there the last line of fund series, if you take, the last line always corresponds to minimum frequency. This was corresponding to maximum frequency in the entire hydrogen spectrum, whereas fund series, the last line corresponds to the minimum wavelength in the entire hydrogen spectrum. Minimum wavelength corresponds to, minimum frequency corresponds to maximum. Highest wavelength will be in fund series, the last line, like that. So comparisons, substitution of these values, remembering the value of R, the key for the hydrogen spectrum. Now let us see one or two important other points also with respect to this de-excitation and the number of spectral lines. Now let us see. Friends, see, I don't want to do any session as a list of formulae and using more and more memory. In fact, here also we can add a number of such formulae for different titles or for different keywords, but all of them, they never come to your rescue in the examination hall. Remember, as I have told you, entire hydrogen spectrum with the two tools with respect to this postulates and then how to write the de-excitation, the different series of hydrogen spectrum. To add to that, only one small thing I would like to tell you, right? This also you need not memorize. There you can use your logic. Supposing example is like this. For hydrogen in its third excited state, how many maximum spectral lines are possible? The entire wording of the question makes it so difficult. What is that? Third excitation level. Earlier when we have talked about the energies, we said ground level, the first level, second orbit, third orbit, fourth state, fifth state, this was the thing. Now there is one more added terminology. What is that? Excited states. Excited means, earlier also we have said that while discussing about this de-excitation, de-excitation happens when it is jumping from higher orbit to lower orbit because of that stability factor or instability factor. Now, when electron in the lower energy acquires energy, it will jump to the higher energy state. It is bound to be present in higher energy levels because of higher energy. Now the point is, excited state is different from the state. See, one more example. This is what we call n is equal to 1. Ground state, first state. Now this is what is n equal to 2. n equal to 2. Now what is the first possibility? An electron in the ground acquiring energy. Now yes, jumping to the second orbit. Therefore n is equal to 2. The second orbit is what is called as a first excited state. In the entire science stream, the terminology is the most essential thing. Remember, terminology is not with respect to English. Beyond English, you will find your physics, your chemistry, or what any other subject. Second state, second energy orbit is what is called as first excited state, and so on. Therefore, now here comes n is equal to 3, the second excited state, and so on. So whenever if I say nth excited state means n plus 1th orbit. Excited state does not convey you the principal quantum number n. So whenever it is said nth excited state, the principal quantum number is n plus 1. Reverse may also be the case according to the data, and that is where reading the question fullest without taking anything for granted. Now when I said this is what is the first excited state, second excited state, and so on. Now here let us also define two important things. As a numerical, this I would like to present it to you. Now already we know that this E1 first orbit, remember, E1 is minus 13.6 electron volts, that famous result of minus 13.6 Z square by N square, hydrogen Z value and keeping different N values. This don't memorize, but there in the examination at least you can do that minus 13.6 by N square values, and therefore now E2, what is that number? You will get by 4. By 4 threes are, and therefore 4s are, you will get minus 3.4 electron. And let me write for one more at least, E3 value 13.6, 9 it becomes 9, 9 1 ja 4, 6 you will get 5, 1 EV and so on. Such that now what is the first excited energy, second excited energy, there comes the point. Therefore now here E2 minus E1, E2 minus E1 is called first excitation energy. Then second excitation energy is not E3 minus E2, it is always with respect to the ground state that we are taking. Excitation is always with respect to ground we are taking. Therefore E2 minus E1, first excitation energy, then E3 minus E1 is the second excitation energy. Now see here, the energies are negative we know because of the bounded nature of this electron and nucleus, the total energy always negative, whereas when you consider E2 minus E1, the excitations energies, they are always positive. Why? Look here, what is that E2 minus E1 number you get? This is minus 3.4 times minus of 13.6, which is, this is a 10.2 electron volt you get, right? Yes, 10.2 electrons, and this number is positive. So the energy level diagrams, when you remember, the numbers with respect to energies and excitation energies are important. So this is 10.2 is the first excitation energy. The second excitation energy is now E3 minus E1 and so on. So all excitation energies are positive. Now we know that these energies are very smallest and convenient units of electron volts are used, right? Now excitation energy versus excitation potential is also one of them. Last time when we was talking about those photoelectrons and all, stopping potentials, maximum kinetic energy, what you did with respect to the units or the numbers, remember, the same we will now discuss as well. Now earlier we said the first excitation energy E2 minus E1, the number is 10.2 EV you got, right? 10.2 EV got with positive number. Now, the relation that we started from electrostatics, the kinetic energy is potential times the charge. Based on that, we did number of examples even in the case of photons or this photoelectric effect. Therefore, now I will say the first excitation potential. First excitation potential. Now since we have this excitation energy directly straight away in electron volt, you remove that E, then it becomes 10.2 volts. So in that excitation energy, if we remove that small E, the energy term becomes potential term. That is what is the principle starting from electrostatics that we have told. So 10.2 volts will be the first excitation potentials. So similarly, the other excitation potentials is an important concept with respect to hydrogen spectrum. Now after that, see one more thing I would like to show you, that supposing, to begin with I have told you a question. What was that? Hydrogen in its third excited state. What is meant by hydrogen being in the excited state? The electron that we are observing is in the third excited state, that is fourth orbit. Hydrogen in ground state refers to hydrogen atom in which electron is in the lowest energy, that is the ground state. Therefore now third excited state, keywords from any of the data. Third excited state means n is equal to 4. Now earlier when we were discussing about de-excitations that I have told you, this is not that all the de-excitations that happen sequentially in this manner. No, all are the possibilities. Therefore now third excited state, 1, 2, 3, 4. Now what are the different possibilities, so that what is the maximum number of spectral lines that it gives rise to? Now what are the different possibilities? N is equal to 4 to 3, one possibility, 4 to 2 possibility, 4 to 1 possibility. Not only this, you remember, this 4 to 3 again can cause 2 more de-excitations, like 4 to 3, 3 to 2, 2 to 1, is it not? Similarly, 4 to 2 also, see, 4 to 2, a direct de-excitation, and then from 2 to 1 is also possible. Likewise, an electron in any excited state, what is the total number of spectral lines that are possible? This is where the Bohr has given, the Bohr atom and the Bohr model was given highest credit. Because the doubt was, if hydrogen contains one and only electron, where comes the question of so many spectral lines that we observe, innumerable spectral lines that we observe in the case of hydrogen spectrum. Single electron giving rise to so many spectral lines. And that is what is the greatness of this Bohr model. Now we will find how these many number of spectral lines are possible with single electron. Different possibilities of de-excitations. Therefore, in the examination, you may not every time possible to write like these de-excitations, different possibilities. For that, I would like to give you one simple expression. What is that? Right. If electron present in nth orbit, I am telling you again, please do remember, it is orbit versus excited. Two things are important. I am telling you for the regular format, like electron present in nth orbit, such that n is greater than 3 I am taking. N is greater than 3, we give one expression. Because n is equal to 3, you can write or what or 1 or 2 possibilities that are there, you can write. For n greater than 3, the maximum number possible, maximum number of spectral lines. Maximum number of spectral lines is n into n minus 1 by 2. So that is what is third excited state. I said 4 times 3 by 2, that number will be 6. So for given excited state, the different possibilities. See, again I am telling you, this is the maximum number of spectral lines. Never take any expression of formula taken for granted, because supposing if I said if it is exciting, it is de-exciting from n is equal to 6 to n is equal to 2 only, or n is equal to 5 to n is equal to 2 only. In such case, what is the different number of possibilities? Then that number is not maximum. Remember, this expression you can use when you find that adjective in the data. What is that? Maximum number of spectral lines, and therefore the de-excitation will be to the ground energy level as well, from higher to next lowest, such that the last one possibility is the ground state as well. So maximum number of spectral lines, this is one simple expression that I am. Likewise, I can go on adding the number of formulae, but no. Just remember all those expressions that we have given in the previous session, and today the two tools in the form of this expression and a de-excitation diagram. Right? So this finishes our concept of atoms. Practice well. Assignment is also shared with you. Hope you are going to each and every assignment. Expect that you call your teachers as well. Clarify any of your doubts. Still weeks and weeks of time with you. Make the best use of your time for your both CET, NEET, JE examinations. Have a great day.